Everyone, hope you're doing well today. Our lesson is going to be talking about two-dimensional rotations into three-dimensional solids as well as cross sections of solids. Before we get into the lesson, I just want to quickly review a couple of key terms, like keywords that represent volume. So words that affiliate with capacity, how much to fill something or how much something holds would then kind of key in that you're dealing with volume. If you see words like you're wrapping something, painting something, or covering something, that then would imply surface area. A label or size represents lateral area. So because we finished up with surface area and lateral area yesterday, as well as volume, Monday and last week, I just kind of wanted to recap those three separate concepts with some keywords. So we are going to work on, or kind of talk through, if we rotate something that is two-dimensional, what three-dimensional shape does it form? So if we were in class, I actually have all two-dimensional pieces of cardboard attached to like rods, and I rotate them, and then you're able to visualize what it looks like. So what I did was I'm going to go through each one and show you through my sketch what it should look like. So here's the first one, and at first we have a triangle. So if we take a triangle and we rotate it about this axis right here, so think about this point staying and this point staying, right, because they're on the axes, they're known as those invariant points, so here and here, these will all stay. Now this point here rotates all the way around, and then all the way around in the back, and it forms a cone. So we rotate a triangle to get a cone. And then there's this little image here. You can kind of see the blue triangle rotated all the way around. Okay, next we're going to talk about rotating a rectangle. So here we have our rectangle. So points here and here and everything between stay. Now this point rotates all the way around, and this point here rotates all the way around. And we get a cylinder. So here's another look at what the cylinder would look like. So here's our rectangle if we rotate along this vertical axis, but also if we turn that axis horizontally and we still have a quadrilateral or a square, we still get the cylinder. Now they just go round and round this way. Okay, so you rotate a rectangle or a quadrilateral to get a cylinder. For this one, I think of a revolving door. If you've ever been into a building, like usually ones in the city or even some office buildings here on Long Island, you push through the rotating door, and if you kind of look on the floor, it has that circular two-dimensional shape, but the whole thing is a cylinder. Okay, and now over here we're going to talk about rotating a hemisphere. So if I rotate, a semicircle. So if I rotate the semicircle, half a circle, these points stay, and then these points kind of go around and around, and we get a sphere. It also works as if you rotate a circle. If you rotate this circle, you also get a sphere. So if you rotate this semicircle along this vertical axis going this way, you get a sphere. Or a circle, you could also get a sphere. Now what's interesting is if I rotate a circle like this, where no points are invariant, it's no longer a sphere. If you take a look, these like kind of orbit around, and you almost get what looks like a tire or a donut. So we're going to leave it as a tire or a donut. Okay. On the next page, what we're going to just look at is if we have something that's also a semicircle. If we rotate it now along this horizontal line, and it goes this way, we now get a hemisphere, half a circle. So that's really just dealing with two-dimensional shapes rotating into 3D solids. So now we're going to take a look at cross-section. So remember what a cross-section is. A cross-section is like taking a slice of a solid. So I kind of have all the solutions here listed. I sketched myself a cone, a cylinder, and I list through what each one's cross-section will be. I'm actually going to go through and show you them. I have a website, and I took screenshots of each piece so that it's easier for you to kind of see what I mean by this. And then we're going to get back here to with the rectangular prism. Really any prisms, talk about the maximum number of sides of the prism in terms of also the cross-section. Okay, so first let's deal with, what do we have first? We'll do the the cylinder first. Okay, so cylinder. So if you take a look what we have, over here on the left-hand side is the solid, and then what you see as like the black outline is the cross-section, and then the cross-section's picture is over here, and I identified it. So if I take a cylinder and I kind of cut through the bases, just like this, straight down, I get quadrilateral. If I take a cylinder and I cut across horizontally, I get a circle. Seems reasonable. Now look what happens when I kind of cut at an angle and I start at the side and go through the base. I get this over here, and if you remember from last year in algebra, it kind of goes up and down. It's known as a parabola. And then over here, if I kind of take my cut and I raise it a little bit so it doesn't go through the base, it goes like from side to side, I get this oval shape or an ellipse. Okay, so that's your cylinder. You get your quadrilateral, a circle, a parabola, and an ellipse. For a cone, we can have a circle by just kind of cutting it across. We can get an ellipse by cutting it from side, kind of to side. We're not going through the base. We can get a parabola by starting from the side and cutting like down across the base. Here's our parabola. And we can also get a triangle from cutting from the straight top, perpendicular to the bottom. I mean, it doesn't even have to be perpendicular, it could be on the side, but we still get a triangle. Okay, so here's our cone. And then we have our prism. So here, this is a cube, but a cube is essentially a rectangular prism. And what's interesting about it is there's a relationship. In any prism, the number of sides, so in this prism there are 6 sides. 6 sides indicates that the two-dimensional cross-section that we get must have or will have 6 sides. So 6 sides tells us it's a hexagon. So the number of faces tells us how many sides in our polygon it's going to have. So since there's 6 sides, we have a hexagon. If it was a prism with just say 8 sides, then it would be an octagon. Okay, so I really like the prism, especially the rectangular prism, because it's kind of crazy. You would never think that you could get a triangle, quadrilateral, a pentagon, and a hexagon by the way you cut it. So again, I just kind of like the visual here. It relates that a hexagon, you know, the 6 sides of the hexagon to the 6 sides of that figure. So you can kind of just take a look, and it is true that you have all of these cross sections. Okay. And then finally, we have our square pyramid. So it means it has a square base, but it's a pyramid. And for that, we can have a triangle, quadrilateral, and even a pentagon. Okay, I know it seems weird you have a pentagon, but here it is. 1, 2, 3, 4, 5 sides to give you a pentagon. Okay, so again, you can use this lesson to kind of refer back to, so you can see the different cross sections also on that page. Right here, I have them listed, what they are. So you have your cone, your cylinder, rectangular prism with that maximum number of sides in a cross section is the same as the number of faces of the prism, as well as then the pyramid with the square base. Okay, and remember, this is a video, so you can stop, rewind, copy, listen again. It's up to you how you want to use the video. So here are just some practice questions to kind of relate cross sections. So for the first one, it says, William is drawing pictures of cross sections of the right circular cone below. Which drawing cannot be a cross section of a cone? So here you have them. We have a parabola, triangle, ellipse, and square. And if you're uncertain, you could always go right back to this and see what don't we have here. And we don't have a square. We don't have any quadrilateral. So we know that for that choice, this one up here, the square, is not a cross section. Okay. Number 2, it says, which object is being formed when this right triangle is rotated around leg RS? So that's the important part. They like to throw these kinds of questions in here, and it matters what you're going to rotate around. So if I'm rotating around this leg here, that means T goes around and around and around. R stays, S stays. I have a circular bottom, comes to a point. That's going to be a cone. Right? Be careful. So many times what's like the mess up or kind of like the distractor is we think pyramid because it's at a point, but it's actually a cone because of that circular bottom. Okay. And then the last question is actually going to be talking about volume. So it says, if the rectangle below is continuously rotated about side W, which solid figure is formed? So, oh, actually, the next one's volume. So for this one, we get a cylinder. So we rotate this around and around, and we actually get a cylinder. All right, now number 4, that one is going to be a volume question. So take a look at how they used cross sections and also rotations to kind of throw in a volume question. So it says we have triangle ABC and it has legs that are 4 and 6. They want the volume of the three-dimensional object formed by continuously rotating the triangle around AB. So they're rotating it around AB. So for these questions, there's no way you can do this in your mind. Like, you have to kind of sketch something. So first, if you rotate a triangle, what do you get? Well, you get a cone. And it's important to know in the cone what's the base and what's the height. So if I'm rotating around AB, that means C is coming around and around. So my circular base is going to be over here. This is going to be the height of my cone. So now if it's a cone, the volume formula is 1/3 pi r squared times the height. Well, AB is my height of 6. And from A to C, well, that's the radius of that circular bottom. So now my radius is 4. Now I look at my choices, they're all in terms of pi, so I know that after I substitute in a radius of 4 and a height of 6, I'm really just dealing with 4 squared times 6, which is 96, and then take 1/3 of 96, which is 32, and I'm bringing down pi the whole way, so I get 32 pi as my total volume. Okay, and that's how they're going to throw in volume for those two-dimensional rotations. Make sure you're aware of this, because when you do have your test, we could ask a question like this. This is fair, right? It takes two-dimensional rotations and also incorporates volume. All right, so again, this video is made for you to kind of decide how you want to go back, look through things, but what we did focus on here were the two-dimensional rotations into 3D solids, as well as cross-sections. If you have any questions, be sure to email me. There is no Google form that goes along with this, because you do have your test this week. So remember, this is a lesson you definitely want to refer back to while reviewing and or taking your test. Hope to talk to you soon.